Hi everyone, I'm Kathy Zitt, Managing Editor of Solar Power World magazine, and I'd like to welcome you to today's webinar on how asset management can maximize your returns on your solar project. And today we'll learn how to analyze performance metrics and identify performance opportunities and create an action plan to execute it. Before we begin, I'll go over just a few general items. This webinar will be available after the presentation on demand on solarpowerworldonline.com, and will also be emailed to all registrants, so you can view it again at your convenience. And you can also download the slides from the resource box. You can have those. And there will be a question and answer session at the end of the presentation, and we can encourage you to participate. You can do so by submitting your questions whenever they come to mind throughout the presentation, and type them into the Q&A box on the bottom left of your screen. And lastly, we encourage everyone to engage in this webinar conversation on Twitter with the hashtag #SolarWebinar. And I'll introduce our presenters. Today, we have Larry Freeman, Business Development Manager of Asset Administration, and Lee Connor, Asset Administration Manager, as well as Eric Orsino, Customer Account Manager, all from EDF Renewable Services. So thank you all for being here, and go ahead whenever you're ready.
Thank you for that introduction, Kathy. It was very generous. Again, so we can put voices to pictures there. This is Larry Freeman. I'm the Business Development Manager and head up our efforts here with the Asset Administration Group. And with us today is Lee Connor, who is our lead Asset Administration Manager, and Eric Orsino, who works as our Customer Account Manager. Lee and Eric, would you like to say a quick hello?
Thanks, Larry. As Larry said, I'm Lee Connor, and I am an Asset Administration Manager with EDF.
Yeah, thank you, Lee. Thanks, Larry. Eric Orsino here, Customer Account Manager. I work within the internal department in the Renewable Services, anything associated to and related with operations and maintenance.
Okay, thank you, everybody. With that, let's go ahead and move to the next slide and dive right into the content. Okay, so what we're going to talk to today is how strategic implementation of your asset management program can help maximize your returns. We do this primarily through key performance indicators, right? That's an often used term, and I think everyone is pretty familiar with, but what we're really discussing here are what are those metrics that really give you a gauge or a barometer, so to speak, of how well your assets are performing and really inform your direction as you dig into the projects and decide the best place to spend your resources. We're going to do this talking about solar, primarily performance analysis, but we are also going to use a wind project for a little bit of financial analysis here at the end of this too, because it's just frankly a much more visible case here. Then we'll talk a bit about remediation plans. So once you've identified a problem, something that you can positively affect improve your bottom line here, we'll then move on to closing thoughts and wrap this up. So with that, let's go ahead and move to the next slide. Okay, so we're going to start with a bit of a primer here. Our first webinar in the series was actually about the tools, the people, and the processes that make an asset manager successful in your group. Here we just wanted to then redefine what we feel is asset management. In some cases, right, a term that becomes very fluid in that it is actually, directing the O&M. Some people consider it just financial. Within our group, we look at it in a more holistic framework, where we're looking at both the plant operations, the finance, certainly the compliance and reporting, and then more of the active management and the warranty management, stakeholders, and then really the analysis, curtailment, revenue, and operation. So there are many things that we always say, quote unquote, that thou shalt, right? You have to have these things done and on time, primarily to prevent further problems from cropping up. And assuming that you have the right systems in place to stay on track, you can then focus your time on bringing value to the project. So with that, let's go ahead and move forward and talk about some key performance indicators. Okay, here we see a little graphic that we had put up to show really only a small amount of many of the different key performance indicators that we use. Some of these are standardized by project across all of them, for instance, EBITDA. But then there are others that tend to be specific to a project, because that is what an owner is really looking for on that one, because they may want to track things differently. With that, Lee, do you want to talk a little bit more about some of these specific KPIs and how we bring them to bear on a project?
Absolutely. As Larry just explained, KPIs are typically just different metrics that are used either to gather a snapshot of how a plant is performing or to get a deeper look into a specific aspect of a project's performance. I think asset managers look at several metrics, but one of the most common key performance indicators we use when discussing the overall health of a project is EBITDA. I think that most folks are pretty familiar with what EBITDA means, but just in case, EBITDA is an acronym that means earnings before interest, taxes, depreciation, and amortization. In simpler terms, EBITDA is the overall revenue of a project minus its operating expenses. And I think the reason that it is such a common metric used in project analysis is that it includes both financial data and operational data. And in this presentation, we can see how a project is performing overall. I think having both financial and operational data can help to direct our project mediation plans. And we'll go through many scenarios later in the presentation about how we determine where an issue is and then how we come up with a remediation plan for that particular scenario. I think we also look at several other metrics such as net capacity factor, weather adjusted performance index, operating expenses, wind speed, insulation, turbine availability, performance ratios, among others, to understand how a plant is performing. Basically, we will check the actual KPI performance and compare that to the budget or the anticipated performance to help us better understand what is happening at a plant at any given time.
That's interesting, Lee. I had a quick question. As you talk about performance, we're all very familiar that both wind and solar projects are affected, by Mother Nature. So can you help me visualize a scenario where weather was a key factor in a loss of production for a site?
Absolutely. Let's take a look at the next slide, and I think we can dive right into that. So this scenario here, if you look at, this is basically a graph that shows monthly performance. And when you look at it, it's relatively hard to determine how the plant performed for the month. Not because the data is missing or because it's inaccurate, which is a common problem that we face. But in this case, it's just hard to see what's going on because there's so many swings of the data. So sometimes it helps to look at the data once it's been consolidated overall for the month. And if we move to the next slide, we can take a look at that. So here, we can see from this table, it does just that. It actually takes all of the data from the month, puts it into a nice clean presentation so that we can start to do some analysis. Unfortunately, we can see that we were about 330 megawatt hours below budget for the month. And the next question asset managers will always ask is, why? This is why we start to look at other metrics to help us determine why the plant has not met its budget for the month. In this scenario, it is clear that when the data is corrected for weather, which is the number in the weather adjusted performance index column, that the plant is performing above budget at 101.7%. Principally, this means that the plant did not meet its performance budget because the sun did not shine as much as anticipated. Unfortunately, in this scenario, there's just not much that a project owner can do. If it's not sunny or if it's not windy, then the production suffers.
So it must be hard to make some assumptions as to problems that are going on. What about a scenario where underperformance is not as readily explained, something where it's not just popping out as being 336,000 kilowatt hours under? Is there a scenario where it's not as obvious?
Yeah, I think if we move to the next slide, we can walk through a scenario where...
Yeah, thank you for that, Lee. That was a really good explanation. And as we look into this scenario, we can see very similar results where, in this case, a smaller project still came in 196 megawatt hours under budget, which is giving us a pretty low performance index. Yet in this case, the numbers show us really quickly that it is not a resource issue or whether the weather amount of sunlight that's causing this, and rather that after correcting for the weather to budget, we see we actually had a greater than anticipated loss. And so here from the table, right, we can see that something happened, but this is a case where this KPI in and of itself doesn't tell the whole story. So from here, this is where we would dig in back into one of those performance charts and see if we can find a really good explanation of what happened. So can we go ahead and move to the next slide, please? Okay, so looking at the graphical illustration here really helps you determine that this is an operational problem. We can see that right around the middle of the month, that we took about a 50% drop in the overall performance of the plant. This is pretty clearly an operational problem. So for discussing this with the site team, it turns out to be, in this case, because of the size of the plant, feeder problem, where we had a whole group of inverters that were lost due to a transformer issue.
All right, so now that you've determined, the problem, Larry, what essentially are you guys going to do about it? You've taken the data, you're looking at it, you're visualizing it in this graph. What are the options moving forward?
Well, so the first step in that is to understand precisely what the problem was. In this case, it was a leaky bushing on a transformer that caused it to fall out. So there's a couple of steps that go in, questions asked right off the bat. The first one was, is this item covered under warranty? If so, do we have guarantees for response time from the OEM to get on site and make the repair? In this case, it wasn't covered as a warranty item, so then we look at what are the parts availability, are those parts in a spare inventory, when can we schedule someone on site, and how can we make the repairs? In this case, unfortunately, we actually saw the problem happening in real time and were notified by our operational team. But then going back, just discovering that this was kind of a unique situation and a low failure rate item that the owner of the project had chosen not to keep in stock. And really that would be pretty common. You can't, as you're thinking about how to best mitigate issues in your plant, you certainly can't have, quote unquote, a whole nother plant sitting on the shelf, right? So you have to look at key spares. And in this case, it was simply a strange or, a low probability event that caused this.
Right. So yeah, obviously, keeping a large inventory or a whole site of spares on site is not feasible. So that's fairly obvious. But not every problem has an easy answer. So, Larry, could you describe a problem that took more digging, something that utilized your team's experience to really uncover the root of the problem?
Sure. We've got a scenario here on the next slide that we can talk about that.
All right, so in this case, if we take a look at the table, it looks somewhat similar to the first scenario where we were talking about the weather-adjusted performance index and how there's really not much to do if the sun is not shining as much as anticipated. So we can see that there basically is a 7.5% improvement in performance when we compare the weather-adjusted performance index just to the regular performance index. However, as the weather-adjusted performance index is still about 1.5% below 100% performance, we want to keep looking to see if there's some other issue at site. We want the plant to perform as close to 100% as possible. So the next step is to look at data graphical representation to see if this helps us determine what's happening. So if you take a look at this slide here, we basically started with a monthly graph, and there was not enough detail for us to be able to determine the issue. So our next step was then to pull this graph, which is basically a daily representation of how the plant looks. And when we looked at this hourly production here, we uncovered data that helped us to see what was really going on at site. So if you look at the graph, you can see a curve mismatch. Not really in the middle of the graph where you see, you know, a bunch of the kind of data swings going up and down. That just shows that there was some miscellaneous clouds going over site. But if you look at the shoulders, you can see how there is a data mismatch there, where basically the orange line and the green lines don't line up. So because we have experience managing these sorts of problems, we know that there are usually only a few causes for these sorts of problems. One would be if we had a project where the azimuth was not true south, then you'll see, you know, a graph that looks like this. In this case, we knew that the azimuth was true south, so we knew that wasn't the issue. If the projects are tracker projects and they have a stalled tracker, it can also show this type of mismatch, which in this case, we reached out to site, had them verify to us that the trackers had not stalled, which they did, so we knew that was not the issue. And then the third type of problem is if the project actually has shading losses, then it will exhibit this type of mismatch. So after doing some basic problem solving, we had determined that there were probably shading losses on site. And so then we go to the next step, which is trying to determine what's causing the shading. So in speaking to site, sort of looking at site drawings, having done site walks previously, we knew that there were trees that were causing the shading. So the next step is, do we then have rights or can we trim those trees? So that's when you go back to your contracts, take a look to see if you have contractual rights to be able to trim the trees. And in this case, per our land lease, we had negotiated in advance that we would have rights to trim the trees as needed. But then, of course, there's always the cost analysis. So how much is it going to cost to trim the trees, and will that really boost production enough to cover the cost? So we did our analysis and determined that tree trimming was well within the payback curve of our budget. And so we decided to get those trees trimmed. I think there are a few takeaways from this scenario. First, ensure that if there are trees close to your project, that tree trimming rights are obtained. And if it's not possible, sometimes you have landowners that really aren't going to give you the tree trimming rights. That's okay. I think you just need to make sure that you build shading losses into your energy assessment and make sure that the project is still going to get enough revenue to meet whatever your particular internal targets are.
And that's interesting, Lee, and obviously your experience within the field and understanding this curve mismatch led to your assumptions or your realization that highlighted the shading losses. Taking that into account, have you guys ever run into a scenario that resisted conventional analysis, something that maybe didn't jump off the page?
I think if we move to the next slide, we'll walk through a scenario that absolutely, Eric, that's a great question. I think as we go through this next scenario, it'll be very clear that it does not fall in line with traditional analysis.
Yeah, and thank you for that, both of you. So as you can see here, going back to our, which should be familiar by now, KPIs, you'll see that we have a very similar issue where we are underperforming, where the weather itself is a small contributor, doesn't explain it, and we're still running about 1.5% below really where we should be targeted at on this. In this case, we followed the similar steps we did before. First looking for any obvious operational issues, any other reason for the performance mechanical issues. And what we found here is that we were seeing a few issues, but they certainly did not make up the full gap, right? And this gets a little trickier to do when you're sort of chasing what I call phantom problems around. So we were able to see that there was, for instance, an inverter fault on the 13th, and by doing a lost energy analysis of that, we were able to look and see that we had approximately, a 0.25% there. And we're able to look at another problem and find this. But, really going back and chasing our tails on this over a 3 or 4 month period, we were still just seeing this persistent 0.75% to 1% that could not be explained. There's always some problem that covers a little bit of it, but we never quite get there. So at this point, we start digging even farther into the issue. Start comparing inverter to inverter performance ratio analysis, both intraday and intraday. Start comparing signals on the recombiner boxes of the home runs. After all of that, really found, again, we were still not finding an obvious answer. And some of the problems when you're chasing these fine-grained performance issues come down to plant design and, frankly, sensitivity of the measuring device. In this case, this was a thin film plant that runs 6 in series, 4 in parallel, right? So what happens is we're running fairly low currents with a lot of inputs. And what we see is these were, for instance, 200 amp inputs or CTs, current transducers measuring the DC current rated at 200 amps. But when you're trying to look for these individual problems, these quote-unquote 1% problems, that is often below the calibrated sensitivity of the CTs. So what I mean by that is you could see that some of them were, a couple amps above, a couple amps below, but when you try to control for calibration, you'd see that the data all sort of washes together. And again, no problem jumps out. So, from here, the next step is to start looking at, we're not seeing a mechanical issue out there that readily jumped out. We're not seeing typical problems. And, ultimately, then we start doing things like individual IV curve tracing of modules. Took a batch of the modules and set them off to Fraunhofer for testing, thinking maybe we're looking at a advanced degradation problem, or something else. And at the end, we are several months into this and still really can't fully explain about what's happening out at the plant.
And that's interesting, Larry. I mean, you're walking yourself through a problem here. You have a very large problem. You're working through a trial and error process where you're testing all the mechanicals. You're doing analysis on inverters, comparing the 2 and 3 and 4 to make sure that they're operating correctly. You're running through calibrations and finally going through IV curve tracing. All of this obviously is coming to some solution whereby you're recapturing some losses, but you're not getting to the root of the problem. Owners typically will not accept underperformance perpetually. So, my question to you guys is, what essentially did you do? How did you correct the problem? How did you come to the root of it and present a solution?
Yeah, so you're right. I mean, that's the answer, right? You can't accept perpetual underperformance and just say, it's a mystery, right? There's too much money left on the table. So in this case, what we did, was went back and pushed the numbers through the model again, right? How big of a problem? And really what I was looking for in this case was, how much money do I have to find this problem, right? At some point you can't just keep chasing your tail and, spending money fruitlessly, right? You start with a low-hanging fruit, and frankly, there just was none here. So at this point, we went back, pushed the numbers, right, and assumed at this point what is, 1% loss looks like over, a period of 3 years, right? Figured out what kind of money this is, and really said, okay, we need to understand what's happening and find ways to adjust, because ultimately you're either going to have to adjust your expenses or get your performance back up. I mean, ideally you want to maximize both of those. So in this case, we came up with a number that seemed reasonable, and then started talking about what we can do with that. And ideally, this problem would have cropped up in the first 2 years of a project when we were looking at having an EPC performance wrap, in which case would have been great, right? You file a formal warranty claim with your data, and then manage the problem through your EPC. In this case, it had already expired, so we really are looking at something that is very difficult to work through. So here what we did ultimately in coming up with this was decided that it was time to break out the big guns, and we went and did had an aerial survey of the plant performed. And so with that, we can bounce over to the next slide and really dig into what that looked like. Okay, so in going with the aerial photographs, I think a lot of people have heard about this, right? It seems to be one of the buzzwords in our industry now that says, great, we can do these things with thermography that aren't possible outside and solve all of our problems. And while that is true, there's still some pretty good analysis to be done, and then what do you do with the final output, right? Much like anything else, there's no, really is no magic wand here. So what you see here, if you can look sort of just to the center of the screen, is a line that is a little bit brighter than the others around us, right? So what does that mean? Well, essentially when a module is exporting power, then it's going to be cooler than those around it. So therefore, if you're having a string of 6 modules, you kind of look to the fuzziness there, you'll see 6 individual dots, is that because those are not making power, that they're hotter than those around them. Now, you would think that this would be possible to see in, with your tools available to your technician, right, a handheld amp clamp, right, doing your normal voltage and current testing. But however, I was saying earlier, this being a thin film plant, we're really looking at high voltage and low current plant designs here. So as a result, even at 1,000 watts per square meter, that string is showing up at less than 2 amps, right? So when you have, for anyone who's ever done this work, right, the technician out in a combiner box, right, with an amp clamp, right, on there and wrapped around the wires, you'll find that how you hold it compared to the wire, is it close to touching others, what goes on, that really those things bounce around and are hard to see. And also recall that when we're talking 30 inputs per combiner box times 1,300 combiner boxes, I mean, these are guys with tools and gals out in the field, and they're not robots, right? So, that's the idea, is that normally you would use your SCADA analytics to tell you where the problem is, send a technician out to a pretty localized place and find the problem, and then, by digging in, they could. But in this case, as I described on the previous slide, it was very hard to pinpoint exactly where the problems were. So here we go, I've got these pictures, and they're great to start with, right? But, we've got to continue to move forward in this.
And Larry, just to highlight, we're looking at an overview picture of a plane essentially taking an infrared photograph of a site. Now within the site, you highlight here that there is a string that is out, and since it's an infrared photograph, it's obviously showing up as warmer than the surrounding sites. We look at that and we can kind of visualize it, but what I don't quite understand is how does this relate to module performance and the performance of the entire park, tying back to our chronic underperformance issue. Is there a way that you can take this picture, sort of visualizing a problem, and extrapolate that into a much larger, more holistic response to our 1% loss?
We can, actually, and if we jump forward to the next slide, we'll get to the meat of what this type of analysis really does for you. Okay, so here what we can see is an integrated overlay of the whole plant, right? As you can see, it's a rather large plant and spread around, and I suppose it depends on how much time folks have spent looking at as-built drawings and site plans to really have an intuitive sense of what you're seeing here. But essentially, each of these larger grids or blocks that we see here is relative to one inverter station. Sort of an easy heuristic would be that each one of these grid blocks represents roughly a single inverter. As you can see, when we took the results of all of the aerial imagery, IR imagery, and then overlaid those with precise locations from an as-built drawing, the pattern you see is that, frankly, there is no obvious pattern, that these problems are spread throughout the plant, which reinforces what we were saying, as I was saying earlier, about the difficulty in finding this type of problem through an inverter-to-inverter analysis, because, as you can see here, virtually every inverter was impacted almost the same amount, to about the tune of that 1%. So, in doing this, what we're able to do, though, and one of the wonderful things about the aerial thermography is it can actually tell you the type of problems. So, in here we had string faults, which again, in a series problem, what we're really seeing in that is that a string fault really represents a module failure or a wiring failure in that string. And again, at low current, hard to get with handheld tools or to see with your traditional diagnostics. There was some individual module faults, though frankly not as many that were really like section faults within the module, which may have been problems that were virtually impossible to find with your normal tools in the field. And then finally, there's a couple what we're calling section faults here. And those section faults were essentially a combiner box problem. The interesting is those do show up in the SCADA, and I think at this point it was a matter of timing that there was a couple of combiner boxes that had been shut down for an unrelated issue at the time of the aerial survey. And they did actually act as a good ability to calibrate and determine what came out of this. So by using this, we're able to come up with the total number of modules affected and the percentage of the plant. And look what we found here, 0.89% of the plant was essentially permanently offline at this point that resisted the normal analysis. So it was great. We found the problem, and now you have to move forward, and what do you do about it? So this is where we can really take the lessons of this to even further. So when we actually got the agreement to do the first aerial survey, we also negotiated a price for a second flyover, right? Understanding that we would need to validate the results so that we could actually get the most value out of this information. So what we were able to do here, because this overlaid with as-built drawings of the plant, was then take and give very specific locations, right? Okay, technicians, field team, we need you to go out to section 3A, row 34, module places 72 through 86, or what have you, right? And go out and specifically address these problems and correct them. What we then did is, after these were all corrected and replaced, and it did take some time. Again, we're talking about almost 3,000 modules affected here, though there wasn't quite that many to change. Once all of these individual connections were confirmed and back online, we flew over the plant again. And at that point, ran a similar survey, and what's amazing is it came back with 0 faults. The plant was 100% healthy. We got our almost 1% of performance back, and what we were really able to do then to maximize the value of the money we spent was then to calibrate our performance model. Because at this point, we now know precisely out in the field, right, what is happening. So, everyone hears the term module mismatch. We know about DC cabling losses. We know about slight differences in inverter and transformer efficiencies. And what really happens is all of those together, when you're building a model based on your as-built, paint a picture, right, of what's happening in your plant, but it is really hard to calibrate that down to the level needed. You know, for instance, maybe it's commonly known, maybe not, but within a batch of modules, say you're using 300-watt modules, right? And they can be sold in 300s, 305s, 310s, 315s, right? Those are actually, none of those modules are ever exactly 300 watts, right? Every batch that is gone is really between, for just to keep it simple, 300 and 304.9 watts, right? So if you have a 5-watt difference over a 300-watt panel, you know, you're looking at about that 3/4 to just under 1% of performance difference across modules within a group. All of this means that, you know, your model is only ever going to be an approximation of what happens. However, by doing this, we were then able to go back to each, and knowing that we were 100% physically complete in producing on the plant, we were then able to go back, which took a lot of time. You know, this is, again, don't want to think this was an easy process. We'll go back and recalibrate the model down to the individual input level, right? So that we could say that, you know, this input is reading 0.5% high, the CT on a string. The normalized inverter ratio is this inverter seems to outperform that inverter, all other things aside, by 0.25%. And you can go back and put these in, and then, you know, as we get to, hopefully we don't see a point like this in the future, but as we go, we can now rely more on our SCADA analytics, right, since we've been able to calibrate it and find it. So this was a happy ending on this project and finding the problems, but it was a process that played out over several months.
Yeah, and you know, I certainly can appreciate the very methodical approach that you took and your team took to a rather unobvious technical problem. You know, but this doesn't necessarily play into my background. I have a background in finance. I can relate to, you know, some of the problems that you're seeing in the field with respect to the operations and maintenance crews. But I'm a little bit more concerned about the money, the dollars and cents. Are there any scenarios where there may not be an operational issue, but something more that's financial in its foundation?
There are. In fact, if we move to the next slide, I think we have a little bit here from Lee, and she can walk us through that.
Thanks, Eric and Larry. Great question, Eric. I think that it's always good to highlight different types of issues, and as you said, we've mostly gone through operational or weather-related issues. However, this one is specific to a financial issue. So I think first thing to point out here is the metrics look a little bit different than these slides that we have previously talked about. This is a wind project, and it's a hypothetical wind project, but let's just assume that this scenario takes place in ERCOT. So when you look at this table, like I said, we have some different metrics here. We've got delivered generation, which is just the megawatt hours that were delivered for the month. We take a look at the total calculated revenue, which is our assumption of how much money we're going to walk away with. In this case, the project has a PPA with a $25 per megawatt rate. So we have done a quick calculation. We can see that for both those metrics, we're doing great for the month. We're 2% over budget. We look at next our operating expenses, and we can see that we have a slight dip there. We're 5% below budget, which isn't ideal, but it isn't horrible. And then we move down to the next two metrics, total bill generation after basis differential, which we see we're at 50% below budget, and then our production revenue after basis differential, which is 57% below budget. As soon as anybody sees those numbers, especially the 57% below budget for the production revenue after basis differential, it's just a discrepancy that we hate to see. It indicates a massive financial loss for the project for the month, and it's just always a hard pill to swallow. So we know we have an issue here, and we know we have a big issue. We've looked at our delivered generation. We know it's above budget. We've looked at our operating expenses. We know that it's slightly below budget, but nowhere near this 57% delta that we see for our revenue. And we know that our total calculated revenue, which we do just to double check, is also 2% above budget. So I think most people would look at this and say there must be something that's going on with whatever this basis differential is. And just for folks who are not familiar with ERCOT or basically any energy markets, basis differential or basis risk, especially as defined in this example, is basically the difference between the price of electricity that is delivered at the project node versus the price of electricity that's delivered at the project hub. In this particular scenario, the project has taken on the risk of covering the cost of the spread between the node and the hub, and they've done that in exchange for getting this $25 per megawatt hour PPA rate, which is a guaranteed rate for your electricity. Unfortunately, and in this case, taking on that risk shows that for this month, it was a huge hit to the revenue for the project. And I think also, unfortunately, when you're dealing with basis differential, there's not necessarily a clear solution. So in the other scenarios we looked at, it was either, weather, which we know we can't do anything about. It was a transformer or inverter issue, which we knew we could go fix. But in this case, because the project has taken on the risk or basis differential or basis risk in exchange for having the $25 PPA rate, there's not a ton we can do. ERCOT has some products that you can purchase, like congestion revenue rates, which can sort of help smooth out some of these issues, but there is no way to fully delete or erase this type of risk from a project. So I think as ERCOT in particular matures as an ISO, and we start to be able to see congestion trends in the Panhandle in particular, that we're able to model more accurately basis differential. And so if a project does take on that risk, I think the most important thing to do is to really have conservative assumptions in your model so that when you have months like this where you're having such a low production, that it's not a surprise.
Yeah, I mean, that's really interesting. I mean, obviously the hope is that we can model more accurately with response to congestion in the future, especially as more systems become online. And thanks for that financial example on basis differentially. That was very informative. So now as we're getting to the end of our session here, I'm wondering if maybe Larry or Lee wanted to move into any closing thoughts with respect to ending our call.
Yeah, I'll take that one here for starters, and thank you, Eric. First, thanks everybody for sticking with us this long. Appreciate it. And I think my closing thought here on this, when we're looking at, the causes, right? There is, as I said before, there's the discipline of asset management requires, many different things. There is understanding the financial implications of everything that goes on, the reporting on that, and painting a picture to the customer, right? Then you have your compliance issues, right? All of the things that need to be done to really prevent you mitigating the risk to your project. But at the end of the day, I firmly believe that the true job of an asset manager is to be able to tell a story and paint a complete picture to the owners or investors in a project. And for me, that's first principles, right? Every thing that we're putting out, every report, all of our efforts go to these couple of questions. And it's really, are you making as much money as you could be or should be, right? And that's where our KPIs and our metrics come in, right? And the answer is, it's not why, right? And we kind of talked about that here. It's one thing to, not be quite there in your numbers, but it's certainly never acceptable to say we don't understand why you're losing money. And so then finally, what are you doing about it, right? And that really is the core. How am I doing? Why am I performing that way, and how are you going to fix it? Well, it's very simple, right, to keep those principles in mind of what we're doing. At the end, the analysis is really multifaceted, right? And it takes a multidisciplinary team with a lot of experience to be able to look in and have enough familiarity both with the projects in particular and with the design, the operation, the engineering, the finance, and the expenses to be able to really go in and understand what those problems are and to do the analysis. And then finally, the real magic is understanding how to apply the limited resources that you have in a project to get your best return on investment. And that's really the key, right? You know, if we could go in and look at KPIs and say, here's a problem, right? And here's what I think we could do about it to return it, right? Well, you know, if that doesn't make financial sense, then, you know, all of the rest of it really isn't quite nearly so valuable, right? You know, there are times when it certainly, you know, who's worked around projects enough has looked at it and said, you know, if I just had, you know, 3x my normal budget this year to go get these problems done, you know, we could nail this project down and let it run well and really focus my efforts elsewhere. The reality is you don't have that money to work with. So, you know, I think that's, for me, always the key is to keep that in mind. Lee, do you got anything you want to close up with?
I mean, I think just to second what you've said, Larry, I think, you know, those three main questions are questions that asset managers ask themselves every day, hopefully, if they're watching their projects every day. And then, like you said, analysis is multifaceted. I think it's important for us to stay abreast of any sort of new technological advances, such as aerial IR scanning or any other advances that the industry makes to help us do a better job. But I think in general, it's also very important for us to stick to traditional analysis like EBITDA and whatever other metrics and KPIs that we use to take a look to see a project's health.
Perfect. And after all that information, I'm sure our audience has some questions, so we'll begin asking those. Remember, you can submit your questions at any time in the Q&A box on the bottom left of your screen. And I'll just kind of throw these out, and then whichever presenter, Larry, Lee, Eric, you feel you would like to answer the question, you can go ahead and jump in. So we'll start with one from our audience asking if you can talk about completing the same performance analysis on a wind project. Is it similar to how you talked through the solar project?
I'll take this one for starters, and I think Lee probably is in a good position to fill in. So the performance analysis is, in my view, very different on a wind project for a couple of different reasons. And some of them very much just have to do with, you know, nuts and bolts and hardware. So, you know, on a solar project, I think generally we are very used to seeing numbers, right, and making the natural mental leap or the assumption that those numbers represent real things, hard things, right? You know, pickles in a jar, so to speak, right? That there is something really hard behind that. And as I see it, or my way of interpreting what goes on in a plant, in a solar plant, really what you are doing is taking proxy measurements, right, to see how everything is running. So, you know, you do have the energy flowing through your meter, and you've got your resource, your amount of sunlight, and your temperature, but really beyond that, right, you know, what the things we're doing is measuring ratios and proportions and relationships, but we're not actually measuring things, so to speak. So that means that there's a, you know, a little bit of, you know, more interpretation into what's happening. Now, in a wind plant, right, turbines have very good measurement devices and very advanced SCADA, and many of the numbers that you have to work with really are hard numbers, right? RPMs, temperature, right? Pitch rate, right? And you're not, you know, so you're seeing those very difficult things. And so when an issue shows up in a turbine, right, you may, you know, at least at the first level, you've got a pretty good idea exactly what your problem is, where it is coming from. You know, but then at that next level, you know, that's where you get into the magic, which tends to be much more hard engineering or software focused to understand what's happening, you know, relative through, you know, why is that power curve off a little bit at the corner? You're pretty confident in your power curve, but then, you know, the why, you have actually a lot of different data to look at. And it is a, a very specialized, profession, and many times I think when you get down into the resolution of a performance problem in a wind plant, you're really relying on your specialist engineers more so than I think that you need to do on a day-to-day basis with solar. But Lee, do you want to take a stab at that as well, or do you have some different views?
Sure. My views are pretty similar to yours, Larry. I think that wind is a more mature industry. I think when you look at a wind plant versus a solar plant, with a wind plant, you've got every single turbine is its own individual, basically power plant, if you will, where when you're looking at a solar project, you've got a bunch of different solar modules, but they all feed through an inverter and go through their main power transformer, where with a turbine, it's its own generator. So as Larry was mentioning before, we have a lot of data points, and assuming that your data is good, which typically it is, I would say higher quality with wind projects than it is with solar projects. It's easier to do analysis in some ways in that you have more data points and you can take a look at many different things per turbine, but you also, to do problem solving, it can be a little bit more difficult. I think most of us rely on power curves, and you can look at power curve for the whole plant, power curve per turbine, and hopefully that is a good place to start, as opposed to looking at some of the graphs that we did for the solar projects. That's typically where you start, and then come up with your remediation plan.
Excellent. Thank you both very much. Another question, what do you do if all the solutions you talk through are not the answer to your issue?
I can start with that one.
Yeah, go ahead, Lee, please.
I think we tried to, in our presentation, sort of highlight a myriad of issues, but obviously we can't go through every single type of issue that exists for either solar or wind plants. So I think, like Larry said in his example, talking about the IR scanning as the solution, I think staying abreast of whatever technological advances there are is extremely helpful, because it can help us dig deeper or look at a plant in a different way. But also, I think starting with what we did and what we outlined, which are traditional issues, is a good place to start too. So I think trying to find the balance between traditional analysis and then staying abreast of newer ways of analyzing really helps us to come up with new out-of-the-box solutions as needed. I'm sure you can add to that, Larry.
Yeah, I would say that I mean, for me, it comes. I'll talk more in general terms. I would say that how you deal with that is to understand that you're not alone, right? There is enough projects, enough really smart people in this industry working on it that it is pretty rare that someone is truly working on a unique problem, and having relationships and knowing both whom to ask and when to ask them is absolutely key in digging through the more interesting problems. And I've also found that we work in an industry where people are pretty typically believers in the sense that they think that this is an industry worth doing, and there's enough room for all of us here. And I found people typically very generous with their time and expertise. And of course, I think the second thing I would add on to that is knowing when it really is time to pull out the experts, right? As I was talking earlier about limited budgets to do things with, right? It doesn't do you any good if early in your analysis, right, say you've got a $50,000 problem and $30,000 to fix it, right, so to speak. Knowing when and where to apply those resources, right? If you immediately look at something and say, oh, there's a problem, right? It's time to call my, my favorite engineering consultant and cut a PO to them, right? And suddenly you spent $15,000 of your $30,000 you have to work with on finding out what the problem is. you just sort of painted yourself into a corner relative to actually having the money to do anything about it. So, yeah, relying on other people and resources, and then knowing when to pull the trigger and and whom to work with at those times.
Okay, thank you. How often do you rely on subject matter experts to create remediation plans, or do you usually create those internally?
I'll take this one for starters, and then let Lee finish up with that. It's kind of a tricky question, as in saying, how often, because it seems to come and go in spurts. There are times when it seems that you can, really go months and months on end where everything is pretty well status quo. And frankly, it's easy to get a little complacent. And it always seems to be the case, which is one of, I guess, the big tricks of being an asset manager, is not knowing what you're going to do when you wake up in the morning, meaning that there's always the problem of the day. But they seem to come in spurts. So, I've certainly seen projects that were well designed and well built, and frankly lucky that have never really had to pull out any type of extra work on, and I've seen other ones that are simply a constant battle. So, I know it's kind of a non-answer, but Lee, maybe you have a little better view there?
Yeah, I think it depends sort of on I think asset management in general sort of demands several different areas of expertise. And so I think every asset manager has a different area that is probably their strongest, and then has become sort of a master of none but a jack of all trades basically for the rest of the different types of knowledge that we need. And so I think it really just depends on what type of plant, what type of problems your plant has in general, and then what your area of expertise is. So if you have a plant that has a ton of basis differential and you've got sort of an energy market expert as an asset manager, then probably they're not relying on any other experts to do their problem solving, but that particular asset manager might have some operational issues that they don't understand as well. And so I think, like what Larry said, in general the industry is pretty generous in sharing knowledge based on everybody's area of expertise, and so it just really depends on the problems and how the asset manager is set to be able to handle those issues. That's also, I guess, a non-answer, but I've had plants where I never really had to reach out to any subject matter experts, and other plants where I really felt like I was relying on experts a lot just because my knowledge base didn't really match the issues at hand.
Okay, thank you very much. I think we have time for one more question here. How do you ensure that you are staying current on KPIs?
That's interesting. Let me see if I understand the question. I think what we're asking here, do KPIs evolve over time? Are we staying current on them? Because assuming that those are static, right, it's a matter of, well, that's your job, right? You're on top of them every day, tracking them, or certainly at least at reporting time and tracking what's going on. But otherwise, as far as I think what's staying current is you have, the idea, do your numbers and the things that you look at evolve over time. And while I would say that occasionally a new KPI or key performance indicator will pop up that may be appropriate to look at a specific plant, or to track a specific problem over time, generally I think that the key ones are always going to be the same, right? What is your revenue, right? What is your expenses? What is your mechanical sort of availability of the plant? And what is your resource, right? How bright is the sun? How much is the wind blowing? And and really with those, perhaps I'm a little old-fashioned here, but I believe that those tried and true metrics are always going to tell you overall how you're performing. And from there, I guess maybe that comes back to relying on new information if there's a new number that comes in. But I would say I don't typically see too many new numbers or too many different new ways of seeing things on a day-to-day project. Once they're up and built, an asset manager's job is to effectively shepherd that project through its operational life and really ultimately to decommission it. So in some ways what we're doing is not terribly innovative in that we're trying to hold a steady course. But Lee, you want to take a stab at that?
I don't know that I have much to add. I definitely agree with your viewpoint, and I think that, like I said, keeping abreast of new developments where we can find a more detailed problem than we could if it's just sort of boots on the ground, people walking around with tools, trying to figure out what's going on site. I think there's always improvements in SCADA. There's improvements in lots of different ways to monitor SCADA to be able to see, top performing turbines or top performing inverters. I think those sorts of technological advances are always helpful because they help us to see what I would consider traditional KPIs, but at a more detailed level, and that we're relying on sort of machines to do that first round of analysis for us. But I think that, as Larry said, we're not necessarily being innovative in that we're not recreating the wheel, we're just improving how that wheel turns.
All right, well, I think that's all the questions we have time for, but I hope everyone enjoyed the discussion. If we didn't get to your questions or if you have additional ones, feel free to contact the EDF team on your own. You can also submit questions even when you view the webinar on demand later, and we will send them a list of questions that we didn't get to today, so they will definitely get back to you. And again, this webinar will be emailed to all registrants, so you can view it again at your convenience. And thanks again to all our presenters for the great information, and thanks to everyone in our audience. You can register for other upcoming webinars on solarpowerworldonline.com. Thanks, everyone.